So can you see my screen? So you were talking about u dot grad u. Okay. So when you consider a fluid particle or fluid parcel, because we are dealing in continuum, so we have a fluid parcel, and uh, assume this fluid parcel which has some fluid in it. So this is passing through space, like we have xyz directions. So this is moving through space. At this location we have some field quantities, like it has a density rho, it has a velocity v, it has a pressure p, it has a temperature t at this location. In the same way, since this is a world of xyz plane, at some other location we do have some other thing, like we do have different values like rho2, u2, p2, t2. While this particular frame, like the control volume, while it is moving, all fluid parcel, while this is moving through the space, it is actually experiencing differences in these physical properties. These are both independent and dependent properties. So these properties are changing in space, and that change in these properties change in these properties is nothing but the gradient. So while this is moving through the space, the change that this particular parcel is experiencing on these properties becomes part of the convection term. So this, okay, when you are dealing with okay, this comes in momentum equation. You might have seen u dot grad rho. This is in conservation of mass. You will get u dot grad t. This you will get in conservation of energy. So basically this is the convection part, and this is the change in that particular property. So this is the velocity with which this particle has been moving, and this is the change of that physical property or thermophysical property that this particular parcel is seeing while it is passing through. So if you have went through the book by Anderson, he gives you a good example. Like if you are hiking on a mountain towards a cave, and you have a hot temperature outside and you have a very cold temperature inside the cave. So there is a temperature change while you are actually moving, because the air has temperature difference. Like the temperature of the air actually varies from the point where you started and the cave. So you are experiencing that change in temperature while you are moving. So that experience becomes part of this convection term.
Basically, it's the change in properties that are experienced while moving from one part to another.
One position to another position, exactly, yes.
Thank you.
So Arvind and Burton join now, Lakshman. So Lakshman will be the instructor of this class. He'll also come and join us in the future classes. He'll be the one working with open form as well. So Sarah has another thing to do. So Lakshman will be joining. Do you guys have any questions? So are you able to upload the homework?
Mozilla Firefox was not able to grow my.
Okay. So Lakshman, Mozilla Firefox, they were not able to upload the homework. It seems
Because of pop-up blocking.
Oh, because of pop-up blocking. Okay.
Okay. Okay, we will take a look at that one.
You just want some explanation about the velocity divergence.
Velocity divergence. Lakshman, did you hear the question?
So divergence of velocity you're asking about? Hello? So you want to know what is the divergence of velocity means?
Yeah, I need some explanation on that.
Yeah, sure, okay. So Um, okay. While talking about velocity divergence, okay, I mean, you know that this is divergence of the velocity. Okay, in my conventions, I am using tilde under the variable just to indicate this is a vector quantity. So, okay, let's see the mathematical definition. So, du by dx plus dv by dy plus dw by dz in 3D. So this is the mathematical definition. Like you can just apply divergence is del by del x I cap, del by del y j cap, del by del z j cap, and then u is ui vj wj, and then just take a dot product, you will get this one. This is mathematical definition. But what does that physically mean? Again, when you consider a control volume, so I mean we basically deal with control volumes in fluid mechanics. Basically control volume, when it has, okay, infinitesimally small control volume, it is small enough but still it has many fluid molecules, so it has some fluid inside that one. When there is a okay, for example, when this is fixed in space, there is a flow that's passing through this and then going out. So velocity that is coming in and that is going out, so that is basically the, that is how we are seeing the gradient in velocity along x direction passing through this particular the control surface of this particular volume. But this doesn't clearly tell, like this doesn't clearly give an idea what does the divergence of velocity mean. I mean the physical explanation. So let's consider another thing where the uh, this particular fluid parcel is actually moving with the fluid, and as you might have already learned from Sarang that in order to accommodate a certain mass, and while it is passing through the fluids, it is subjected to the forces also, and it has a fixed mass in it. So this, because of the surface forces and body forces, mostly because of the surface forces, it undergoes deformation, like it changes, it undergoes deformation. Either it elongates or increases in volume or decreases in volume just to accommodate the amount of mass. So all this is happening because of the velocity, that's velocity gradient that's happening around its control, around the surface. So physically the divergence of velocity means, what does it mean is the change in the velocity, the change in the volume of this particular control volume while it is undergoing the like fluid flow process. That is a physical meaning that you can see, and mathematically you know this one, this is a direct definition. So in order to be more clear, did you understand what I said, or did you want to do you want to have a discussion? If you start a discussion, we may be more clear.
What was it okay?
No, you can start a discussion. You don't need to feel like I mean, even when I am in the university, sorry, when I started work, I started learning these things, I try to understand what professor says and then thinks that okay, that is enough for me. But that is not how you should learn. You should actually try and ask questions like I mean, did you try to physically see the, okay, while you have a uh, okay, maybe a, okay, while you have a bubble, have you guys watched Passengers movie?
Which one?
Passengers?
What passengers?
Oh, movie. I'm talking about movie Passengers. Okay. Have you guys watched Moana?
No.
Okay. Have you guys watched any movie where they like, okay, any space movie where they show fluid, okay, in space, for example, when you can see that okay, when you just release water outside, it just goes to the top I mean, it just flows around and then it continuously deforms itself. Maybe I can try showing a video there.
The body is moving in a fluid due to change of the area of the body. Change in velocity is called the velocity gradient. Sorry, divergence.
Okay, can you repeat that part again?
If a body is moving in air, there's constant change of
So so that's one kind of interpretation. So if you see, I gave two examples. One is fixed, another is moving. So in moving, like if you consider fluid particle, it is subjected to forces every time because it has fluid all around it. It's just passing through another fluid region. So it is subjected to forces here. There is a shear stress here and some pressure here. So this will continuously deform. So there is a like this will continuously deform, elongate, compress. There is a change in volume here. So the physical interpretation of divergence of velocity is, one thing is change in volume. That's one thing. Another thing is this is a straightforward. If you ask a mathematician, he will just see it like this. And if you try to see from a fixed reference frame, like control volume is fixed, it's the fluid flow inside and fluid flow outside. It's a have you went through the divergence theorem in earlier classes? Did you guys go through divergence theorem?
Yes, we have gone through it.
Okay, so what does divergence theorem says? If you integrate over a control volume, this one, it says this is equal to summation of fluxes passing through all the surfaces. So the amount of the change in the property inside, the change of this particular property, which is velocity, inside this control volume is equal to the fluxes passing through its control surface. That is what divergence theorem says. So divergence of velocity is basically gives an estimate of the velocity gradient, or the, okay, here we are just talking about the velocity gradient, divergence of any quantity, assume it in general, the amount of that particular quantity that enters through its particular surface and leaves through through its surface again. So there is a net change in that particular quantity through that is happening through the control surface. That is the divergence of a particular quantity. And here in the context of velocity, it says that the change in the control volume is also a measure of divergence of velocity. So divergence of velocity has many different physical interpretations and mathematical interpretations. This is one such thing. So my whole point is, don't just limit yourself to one such thing, that's all. In your classes earlier, you might have learned about this one alone, like change in volume is equal to divergence of velocity. So if it is hard, or if it is sort of not understandable, that's okay. But for now, just remember the change in the volume can also be measured by computing the divergence of velocity. Change in the control volume, so yeah, volume of the control volume can be measured. I am not saying is equal to, can be measured by computing the divergence of the velocity field. So it's not just one, it's not the only definition, it's one of the definitions.
Okay, Lakshman, I think we have 6 people, so we can start.
Oh, okay, sure.
One thing, are you recording?
Yeah, I am.
Okay, thank you.
Okay, so okay, I think we are going to talk about lecture 4. I opened it. So I went through this particular PDF. I don't have presentation with me. So it looks like Sarang has reviewed partial differential equation types in earlier classes, and today we will be deriving momentum equation, conservation of momentum. and a little introduction to programming, which you'll be using Octave. I'm assuming you might have installed Octave. If not, we will see a bit. I will not go through the detailed process. I'll just go through a bit. So PD types, as you might have studied, there are three like um, generally used partial differential equations which are applicable for computational fluid dynamics. So elliptic, hyperbolic, and parabolic. And like you might have already seen, like Sarang must have written second order differential equations. I mean, this is a very basic thing that you will learn in undergrad and Wikipedia and standard textbooks. Everywhere you will see this one. So for example, if you have a second order equation like this, then you compute the determinant, which is this one. So based on the value of this, which is less than, greater than, or equal to 0, you will identify whether that particular partial differential equation is it becomes part of hyperbolic class, parabolic class, or elliptic class. And you might have already seen an examples, like for hyperbolic you can see a wave equation which is like del 2 u by del t2 minus c square del 2 u by del x square. It is also a standard definition. And parabolic equation, which is like a heat equation, del u by del t minus k del u square by del 2 u by del x square is equal to 0. And elliptic equation, which is a Laplacian equation, like divergence of grad u or del 2 u by del x square is equal to 0. Or Poisson equation, just the difference is you between Laplacian and Poisson is you don't have like, okay, this is a Laplacian equation. If this is not 0, that is Poisson equation. That's all. So that is in briefly about the PDEs type. So if you do you guys have any questions on this one? This is just a review. I'm not going in detail. I'm assuming Sarang has went through these things. Any questions on this one? No? Yeah, anyone can randomly say yes, no, anything. Just feel free. Okay, so we are directly jumping into momentum equation. So conservation of energy is the fundamental thing before momentum equation, and that is already derived in previous class. So just to give a slight just to write the for the sake of completeness, of course. So d is the density, and this is in vector form. Velocity is equal to 0. So can you guys tell me what is the notation that Sarang has used for velocity in earlier classes?
Vector symbol above you.
What?
You for vector use a symbol above you.
Oh, you mean like this? Oh, okay, sure. Yes. Okay. Sorry about that. Okay. So this is the conservation of mass. This is the general equation. This is the most fundamental equation. This is also called continuity equation. This says that mass is conserved. So this is written in conservative form. As you can directly see, there is no substantial or Lagrangian derivative. So this is temporal derivative, and this is the divergence of rho u. This is not the convection part. The convection part is when you expand this one, u dot grad rho plus rho divergence of u. So when you expand this one, you will get these two. So this is the convection part, and when you combine this and this, you will get the substantial derivative, which is d rho by dt. It is also known as Lagrangian derivative. Okay, this is conservation of mass. Now let's go to the conservation of momentum. Today we are going to derive that one. some basic notations as were presented in this presentation. So did you guys go through this presentation?
Yes.
Okay, I mean, I'm assuming some of you may not, some of you does, but we'll go through everything. So u is the x component of velocity. Since you know u is a vector quantity, it has three dimensions, u, v, w. So that's the basic notation. And okay, we'll be using the following terms like pressure and tau. It stands for the shear stress. It's basically a stress tensor. It's not a vector, so you know the rank of tensor is 1 above the rank of vector. So here the notation that we follow is we have a pressure P which is being exerted by neighboring fluid elements on the control volume or the fluid element that we are going to consider. And same way with the shear stress. So okay, I think there is a spelling mistake here. So this is pressure. So let's assume a fluid particle. You see this yellow guy here, so that is where we are concentrating. So it's not that everything is cubes here. This is just for the sake of simplicity. Your instructor might have drawn this one, so it can be any arbitrary shape. You don't need to worry about being a fluid element should be of this particular definite size. It has no structure. Fluid has no structure. So this yellow guy, that is where we concentrate, and these blue guys are the neighboring fluid elements. Now these are the basic conventions that we are following here. So here pressure from neighboring fluid acts on the control volume. You see this guy, yellow guy here, that is the control volume. So we are changing, if you have observed, we are changing or mixing the usage of some terms, like you can see fluid volume, control volume, fluid element, fluid parcel, all those things represent the same thing. So and here we assume that, okay, if you try to make a free body diagram, so for example when you are in high school, you must have learned a free body diagram. When you have a general body, a gravitational force, so mg acts through the center, and if there is a tension here, if it is attached to a string, that is tension T. In the same way, the yellow guy that was considered in the previous slide, so there are forces acting. So this is pressure force, sorry, a force due to pressure. So pressure is a scalar quantity, it has no direction. So when I give the direction, that direction is determined by the normal component of the area of this particular surface. So again, P, you cannot write a vector to denote P, it's a scalar quantity. So this arrow signifies the normal surface area of this particular surface of this particular area plane. So this is the pressure force acting. So neighboring fluid elements or fluid parcels or control volumes, they are exerting force on this particular control volume, and they all try to exert force in this particular direction. Like that is the pressure. You can't pull like something out. Its pressure is, you are exerting some pressure means you are exerting some force on that particular object, and on that particular, that phrasing on that particular object means the direction is like this towards that element. Now we have, okay, looks like in this particular derivation we have considered a moving control volume. So so in earlier Sarang must have taught about fixed control volume, moving control volume, and he must have derived conservation of mass in all those two frame of references, conservative form and non-conservative forms, and he must have shown you that all forms, that whatever forms that were derived, both conservative and non-conservative forms, both are actually one and the same. By applying some basic vector calculus, you will get one and you will get both of them. For example, what I mean by that is the same vector calculus that we have applied here. So this is a conservative form, and once we expanded this out, we got the substantial derivative, and the resulting equation will be a non-conservative form. Here we are going to consider a moving control volume, And anybody asked any question? No? Okay. So direction of pressure, as you can see, so the pressure is being acted on this particular surface. So this is the direction of pressure on the control volume. By the control volume is the blue arrow, on the control volume is the red arrow. And you can see, okay, so he has considered x, y and z. So this particular plane, the highlighted one, is the area of that plane is dx multiplied by dy. This is a standard formula. So now you can see that from the definition of pressure, the force exerted on this surface due to the pressure is nothing but pressure multiplied by the surface area of this particular element. So pressure multiplied by area, which is the standard definition of the force. And okay, he just expanded. Area is okay. Looks like the convention has changed here. So x, y and z in this particular figure. So now it has become dz dy. Guys, don't get confused about this convention change. Here there is x, y, z in a different directions and x, y, z here in different directions. So I will follow this one. So x is to the right, y is to the top, z is out of the page. So area of this plane is d by dz. And the same way you are seeing on the right side also. So basically pressure exerted by the other neighboring surfaces is towards this one, is the blue arrow basically. So that is the pressure that is being exerted by the other fluid elements. And now okay, so this calls for a little discussion. So have you guys gone through Taylor series expansion? Yes? No? Yes? Guys, you can freely say if you guys think I'm going too fast or I'm missing stuff or I'm saying something wrong, just speak out. Okay. So in the previous slide, like here we have considered p dy dz. So this is x, y and z. So the force, okay, this is this plane. We are actually seeing this particular plane dy dz from through this z direction. That's why I just considered this plane, a 2D plane. Now p dz dy, I'm sorry about this writing. So this is the force due to pressure acting at this plane, acting on this plane at this particular location. And as you might have observed, this is the origin basically. This is the origin. So we have assumed this is fp. Now the distance, the length of this control volume along x direction is dx. So now from Taylor series expansion, this quantity fp can be used to predict force at this particular location. Basically how? It's nothing but fp here plus there is a change, there is a gradient. Assume the gradient of this particular force fp is df by dx. So I considered partial derivatives because fp is a function of both all three coordinates and time. So I just considered a partial derivative, and with respect to space and with respect to x, because we are trying to predict the force along x at a different location, which is dx away from this particular location, so on this particular plane basically. So df by dx multiplied by dx. So this is the value of force at this particular location, which is dx away from origin. Basically at origin the value is fp, at dx fp plus df by dx, sorry, this is del f by del x multiplied by dx. This is not the exact value, by the way. If you have went through the Taylor series, there are higher order terms that are being neglected here. So whatever the equation that we are deriving now basically assumes that the higher order terms are being neglected. You guys should remember this one. So whatever the equation that we are going to derive is not exact, so that is being approximated up to first order quantity, and that is good enough to give excellent results. So we consider only up to first order terms. So this multiplied by the area of this element is dy dz again. So this is the force acting, sorry, force due to pressure acting on this element. So when we go back to the slide here now again, you can see F2 is equal to F plus df by dx multiplied by dx. So this is the force, and that is being changed like I said, with the Taylor series expansion it has become like this. Now okay, this is all about pressure force. Okay, we are directly jumping to the shear force. Okay, I will talk about body force later. Okay, let's talk about shear force here. So you can see normal stress tries to elongate the fluid, shear stress tries to deform the fluid on one side. Okay, so this is the pressure force which is done. You guys are, I mean, this is pressure, this is standard pressure which we have been learning since childhood. Now the stress tensor, let's have some notations for that. So when you consider a control volume, so assume this is the box, okay, so this is along x, this is along y, this is along z, this is the origin. So you know that I used dotted symbol basically by following drawing rules, because this is behind the scenes and this is the one that is visible to the viewer. So now this is the origin. The stress tensor basically happens because of the viscosity, and from Newton's law of viscosity, so from Newtonian principle, for a like the stress contribution, the stress force because of the velocity gradient and due to the presence of the viscosity, you must have read the standard definition. So mu du by dx or mu du by dy in the y direction. So this is the shear force you will see as you go to the top. So if you slice through any layer, this is across a particular layer. On this layer means this one, so this is the layer, the top face is one layer. So if you slice through that one, there is a shear force here like this because of the velocity gradient, horizontal velocity. There is a gradient of that particular horizontal velocity. We are only talking about horizontal velocity here. So now because of that there is a force, because it's basically shearing this particular element here, and on the bottom face it is also shearing. We will talk about why I'm using left arrow here, why I'm using right arrow here. We will talk about them. So here the purpose of mentioning this one is to write the convention. So here for this particular thing I will write tau y x for this particular face, top face. So why I have written tau y x is, so this is the plane where this force is being acted. This is the top plane, by the way, if my drawing is not clear. So just to make it more clear, okay, this is the top plane, and the shear force that's happening on this particular surface is tau yx. The convention is y is decided based on the normal vector of this particular plane along which it is being aligned. So this is the plane and the normal vector points along y direction for this particular plane, so tau y, and then this force is acting along x direction. So that's what x is. So following the same thing, if you guys like, if I have to ask you guys to tell me the shear force on this particular face, basically this particular face is the right face. uh, I'm not sure whether it's clear to imagine or not. Let me make some convention. So this is A, B, C, D. So on the face A, B, C, D, if I want you guys to uh, tell me the notation for this particular shear stress. Basically here the shear stress is actually like a friction on this top face, is actually like a friction. But here on this particular face ABCD, it's like pulling it to, or pulling it outside. So following the same convention, this particular face, the normal vector for this particular face is pointing along x direction. So I'll be writing tau x, and this particular force is along x direction again. So xx. So this is tau xx, this is tau yy. In the same way you can write for all other faces. So if you guys have doubts again, I mean it will not be clear in just one shot. You guys need to practice obviously. So we will just do some other exercise again later. So the here I would like to take this opportunity to mention about these two forces. This is basically a shear force. This is a This is a the tau is a stress tensor, and then here this is acting as a friction shear. It's shearing. So this is called shear stress. And this one, it's actually pulling this one out, like the pressure force. This is acting in the normal direction for that particular plane. This is called normal stress. This is called shear stress. And both of these combined, when written in a tensor form, becomes stress tensor. So basically you have a normal stress and shear stress on each and every face. That means on the face ABCD you do have a shear stress here. So if following the same convention, if I want to write the tau notation for this one, it's tau. And since this particular plane is the normal for this particular plane is parallel to x-axis, this is tau x, but this particular shear force or shear stress is along y direction, tau xy. So at any given plane, so on any given plane you have both normal and shear components. If you want to talk only about x components, you have to see only the x, you have to extract only the x things. So on the bottom face you will have x thing, on the top face x thing, on the back face x, front face x. Every direction you will have x components, y components and z components. We will consider only x components here. So this is about the notations and the shear stress tensor in short. So guys, if you want me to repeat again, you should ask right now.
Hey, Lakshman, that's the question.
Yeah.
Actually, you are mentioning tau xy, right? Xy or yx. The normal direction, is it just for the sake of rotation, or there is some force acting on that y direction?
Okay.
Ix.
So there is a force that is acting, and whenever there is a force, we have to follow some convention. For example, if you have a body, okay, this is a cricket ball, which is, I mean, assume when it is hanging over with a string, okay, with a spring here, there is a force we write in a free body diagram mg, and then tension we write. Why do we write mg pointing downwards and then tension pointing upwards? And we know that while writing this one, we write T minus mg is equal to 0. Why do we give minus for this one? It's basically convention. We followed that. Positive y direction is y pointing to the top side. So anything that points down is minus mg basically. So this is the convention that we adopted for this particular problem. Same way, the convention that we have used here is just the convention. and when we stick to this convention and follow all rules, everything falls nicely. Now to your next question, whether there is a force here or not, or this is just a convention. This is both convention, and yes, there is a force here. Remember, here in this particular diagram you have some 4 elements here. So these fluid elements are actually moving around, like pushing this one, pulling this one, just shearing this one, everything, it's happening on this fluid element. All kinds of forces are happening. So S, the force that you are seeing here, is also part of the stress or the friction or the force that is induced by this neighboring element on this element. So yes, this is actually a real force that's acting on that particular body. Is that clear? Just to see in action about this shear force that is happening here, so I just made a little animation. You can see that by following the same convention, when the bottom is being sheared to the left, top face is being sheared to the right, and this is how the control volume will be deformed. So this is a very minor demo that's I've showed here. Okay, now I again did not talk about why did I follow, why did I keep right side arrow here, why did I keep left side arrow here. Walid, is your question related to why the direction is like that, or is there a force actually happening there and the convention?
Is there a force? That's what my question is.
Okay, so yes, there is a force, and now you should also ask why I followed that convention, why I kept the arrow to the right side on the top face. So the why I kept it like this is also a convention again. So in this particular derivation, we will just assume, okay, every derivation can be derived in a general terms, but when it is general, it should be applicable for a particular scenario also. So now so the statement that we use for this case is without loss of generality. That is the thing that you will hear in mathematics mostly. So here, since the equation that we are going to derive, the conservation of momentum equation, which is general, so we are going to derive that one. If that is general enough, that should also hold for a particular case, and the case that I have considered here is, for example, you have a velocity, horizontal velocity u. We have considered that u is increasing as we go along x direction, and u also increases as we move along y direction, and u also increases as we move along z direction. That is the convention that we followed here. Now, what does that mean? So I mean, I'm just saying that one, so that doesn't give you any information. So let's see what does that mean. Now again, I'm going to the 2D plane. So again, this is x direction, this is y direction. So as you can see, I just used this particular plane. So this particular face, so the back face that you are seeing here, that is the only thing that I have used here, and this is the origin. So this is the origin O. So now one second. Okay, I'm sorry for that. Okay, so I need to redraw again. So let's consider this plane again, x, y. This is the origin. So now when I said u is increasing along x and increasing along y, let's consider increasing along y. So u increases along y. What does that mean? So when you have a velocity here at this particular, so let's consider, okay, this is the y-axis, right? So this is the y-axis plane. Okay, I will draw on this particular face. So let's consider the element, fluid element here, fluid element here, fluid particle here, fluid particle here, here and here. So at all these locations, let's consider fluid particles. When I say horizontal velocity is increasing along y direction, assume there is a fluid velocity here at this particular location like this. So this indicates both magnitude and direction. This is pointing along x direction, and the magnitude is the size of this vector. Now at this particular location, it should be more. The length of this vector should be more. At this location, it should be much more, and at the end, it should be much more. So if you can see here, the velocity is actually increasing from bottom to top. So if you want to write in a differential terms, like from a differential explanation, you can write that du by dy is greater than 0. So did you guys get why I wrote this one? So it's basically du by dy is, if you consider at any given location, u here minus u here divided by y here minus y here. That is the first principle approximation. That is approximation based on first principle for this derivative. It's a basic calculus. So u here, u on the top minus u on the bottom is greater than 0 because u here is more than u here, and y on the top minus y on the bottom is also greater than 0. So this quantity is greater than 0. So by this definition, so because of this, the du by dy is greater than 0. Tau here is in this direction, tau. So basically, when you consider this element and there is another element which is on the top here, so this element will move with some velocity and the top element will move with much more velocity. So the top element is actually trying to pull this one towards the right side. So since we are making a free body diagram for this particular element, the force acted on this particular body by the top body is towards x direction, positive x direction. That is the reason why I have considered tau yx on the to the right hand side. So in the same way, in this particular entire derivation, what we will assume is u increases along x, y and z, positive x, y and z directions. V increases along positive x, y and z directions. Same way w. So using these three assumptions, use these three rules. Basically, this is not restriction. This is just one of the scenarios. That's all. Whatever the derivation that is presented here, if you guys try to follow a different convention, like u is increasing along x but decreasing along y but increasing along z, v is increasing along x, y but decreasing along z. If you follow some random convention and if you derive this equation based on whatever the derivation that I'm going to just show, you will get the same answer. So that is the conservation of momentum equation. That is general. Basically, we are, for the easiness, we are considering just one case. So okay, so whatever I said just here is the same thing that's written here. Velocity uv and w increase along positive y and positive x, y and z directions. So
do you guys understand what he's saying? Sure.
yeah, tell me.
Actually, when we say velocity, weight, quantities like this,
Yeah.
I can indicate the meaning of those quantities. But regarding momentum, can you explain it? Momentum, the meaning.
So okay, momentum. What is it? So okay, momentum is a quantity that is defined to actually identify the inertia of a particular body. So when you have a object here, assume this is a solid body. We will talk about fluid again. Assume this is a solid body. So what is the basic definition that you have read? It's mass times velocity. So if the solid body is actually moving with a velocity u and it has a mass m, so the momentum of that particular body is mass times velocity, and the rate of change of this momentum is defined as the force. That's all. So that is the definition given for the force, and the momentum is the fundamental quantity when compared to the force. Now this is a solid. Now for a fluid, again you will have momentum, because any object that is actually moving has a momentum. So here we have a fluid parcel or control volume, so through which fluid is moving, or this particular control volume is moving with the fluid. So basically fluid is in motion, and you will have, if you can get mass of that fluid quantity and you know the velocity, you will get momentum. You can write momentum. The only difference here is this mass is written as a function of density times volume in fluid terms, because density is the fundamental quantity for a fluid, and then volume is changing with volume is not a fixed quantity for a fluid. It just changes. It's based on the convention that we follow. If we use a control volume and fixed in space, volume is fixed. Otherwise volume is keeps on changing. Here volume is fixed, here volume is changing. So basically it just comes down to the same definition that we have been using since high school. Any object from which we can compute mass, and if it is moving, it has a momentum. That's all.
Kind of intuitive.
Actually, from what I understand, it is the rate of change of momentum that's what is force.
So okay, see, when you have a, okay, you can see this left to right and right to left both, but if you actually go to the core of it, okay, when there is a particle that's actually moving through space, it has a mass and it has a velocity, it is just moving through space, so it has a momentum at any given instant in time and space. It has a momentum. But when you are talking about when there is a force, then there is a change in momentum. That's kind of one way to look at it, but I think the more fundamental way, I mean, which is what Newton's second law is, F is equal to mva, to look at that one is, if you sit on that, but if you just observe that particular particle, it has a mass and it has a velocity at a particular time, and at a different time it has a mass and it has a different velocity. So and that means at one instant it has a momentum m1, m multiplied by u1. It has at a different at the next time it has a different momentum m multiplied by u2. So there is a change in this momentum. What has caused this momentum? In order to answer that question, Newton has, like, Newton's second law dictates that, okay, there is some force that's been exerted on that particular body, which resulted in the change in that momentum of that particular body. So that is the way to look at it. So its momentum is a fundamental quantity, and then rate of change of momentum is force, which is a derived quantity. Okay. Okay, so now we talked about velocity, we talked about, okay, we talked about convention for the stress tensor, we talked about the signs that we are going to use for the velocities, and okay, earlier we have considered pressure force on this particular body. Now we are going to consider shear force. Here considering shear stress only. Okay, so basically only just the shear. Okay, I just talked right now. So this is basically tau yx. So this is tau yx if you have x, y and z. So this is the force that is being exerted by this blue element on this y element on the top face. It's trying to push it to the shear it to the right side. And since based on the convention that I mentioned, velocity is increasing in the y direction, so basically this top element is moving to the right, this bottom element may be moving to the left or moving to the right, but slowly when compared to the yellow element. So since when you are sitting on top of the yellow element, the blue element is actually, the relative velocity is actually moving to the left. So since this has a high, yellow guy has a higher velocity than the blue guy, when you, with respect to this particular this yellow guy, you will see that the blue guy is actually moving to the left, which is like it's a relative velocity that we have studied in high school. So when this guy is moving to the left, that means that this blue guy is trying to move the yellow guy to the left from bottom. So that's why you have this arrow to the left side. That's all. Okay, and now there looks like a free body diagram for this, I mean showing all particular forces on all faces, only that align only along x direction. So you have a pressure force. Okay, let's take a look at this one. This is the origin. This, okay, I think he even used, so this is a b c d e f g h. Okay, and you have x along this direction, y along this, z along this. Did you guys take a look at this figure? Okay, if not, that's fine. So could you guys see this figure clearly?
Yes.
Okay.
Sir.
So if you guys can see this figure clearly, everything, it just sums up the forces conventions that we have used, we have mentioned earlier. So for example, take this particular face, which is A D H E. On this particular face, we have a pressure force P multiplied by dy dz acting towards the positive x direction. Why? Again, because we have a fluid element which is sitting to the left side, which is trying to exert force on this particular body. So this is the pressure force exerted by the left fluid element on this particular fluid element. That's why it's pointing to the positive x direction. And the same pressure force on the right face, which is dx away from the origin. So this is the pressure force. Again, we have used Taylor series expansion and truncated up to only first order term. Again, there are plus second order terms which are being neglected here. So this is up to first order term, and this is the force exerted by the fluid element which is sitting on the right side on this particular fluid element. That's why the pressure is acting to the left. So this is pressure force. And again, the shear force. Okay, on the top face we have used tau yx. Okay, so on, since this is the origin, where is this one? Okay, tau z. Okay guys, there is a mistake here. This is written as tau zx, which is obviously wrong. So this is a bottom face. If you can see a b c d here, it is written, the shear stress is written as tau zx dx dz. This is wrong. It is tau y, because a b c d, this is the plane and its normal vector points along y direction. This must be tau y, and this force, the shear force, is pointing along x direction. It doesn't matter whether along positive x or negative x. Here while we are writing tau yx, it's just the convention. So this must be tau yx. This is not zx. This is wrong. And as we have seen above, the bottom fluid element is trying to pull this element to the left side. That's why it's pointing to the left side. And the top face is dy away from the bottom face. That's why from Taylor series expansion we get tau yx plus del tau yx by del y multiplied by dy, because this is in the y direction. This element we used dy along the y direction. That's why the Taylor series expansion uses yth derivative multiplied by dy. And since this is just a stress, you must multiply it with area to get force, and the area of this particular element is dx dz. So this is the stress tensor. Same way you have the normal vector, normal stress here, which is tau xx plus the its gradient, because this is the origin. We use tau xx dy dz here as the reference thing. And then this right side element, which is dx away from the left side element, you get d tau xx plus the Taylor series expansion gradient here. So now you guys have, like, we in this particular figure it is document, it is mentioned, so like all all surface forces pointing along x direction are being mentioned here. All surface forces means pressure force, normal stress, shear stress are being mentioned here. Body force is not mentioned here. Body force is gravity, here it is not mentioned here. So now since we have mentioned all the surface forces acting along x direction, now let's make a force balance. Okay, so shear stress direction. Okay, this is the same thing like I already mentioned this where is this one, this Taylor series expansion for the force thing I have mentioned. The same thing in this particular slide, the Taylor series expansion is used on the stress tensor or the shear stress force. So basically the Taylor series expansion holds for anything. It's just a general quantity, it holds for any quantity. So okay, these things on this particular of planes, it is best for you guys to practice again and ask in next class for this. Like, just take an example like how I did, consider a plane, and then since the back plane is the origin, so that is the reference, so tau zx acts on that back plane. So and the front plane which is dz away from the back plane, you will again apply Taylor series expansion, you will get this term again. So the force acting on the front plane. So just do practice on each faces, on all directions, on both normal and shear components. If you guys practice once or twice, you will understand and you can ask in the next class again. So now it looks like okay, equation is written directly. Okay, let's derive this one. So that was written directly, so let's derive that one. One second. Okay, now for this particular control element, control volume, we have seen that. So basically for this particular face, right face, I think if we write A, B, C, D, E, F, so this basically C, D, E, F. On C, D, E, F, pressure is acting like this, P plus del P by del X dx multiplied by dy dz, and the normal shear stress is acting like this because we have considered the fluid horizontal velocity is increasing along x direction. So u du by dx is actually increasing when you are going in this positive direction. That means this fluid element is trying to pull this element to the right side. That's why you have normal stress tensor pointing to the right side. Again, this all comes from the convention that we have used. We have assumed that horizontal velocity, vertical velocity, and z component velocity are increasing in positive x, y, and z direction. For this particular arrow that I have written, horizontal velocity u is increasing along x direction. That's why I have written like this. And the value is tau x x plus del tau x x by del x. Okay, there is a dx that I am missing here, multiplied by dy dz. Now we have seen on this particular plane. Now we must see on the left plane also. Actually, to be more like, to be clear, I would have written left side first and then right side. So that way it would have been more clear, because these terms that were obtained are basically Taylor series expansion made on the left hand side terms, made from the left hand side terms. So basically on the left side, the pressure force is acting to the right side because fluid element on the left side is exerting force on this particular fluid element. So it's P multiplied by dy dz. Dy dz is the area of this highlighted element. And then again, normal stress tensor is acting to the right side because again the velocity on the left side is less than velocity on the right side, so velocity is increasing towards the right side. That means the fluid element here is on the lower velocity, has a less velocity than this fluid element. When you sit on this element, the fluid on the left side is trying to go backwards. That means it's trying to pull to the left side. The fluid element on the left side is trying to pull this particular fluid element to the left side. That's why the normal stress force is acting to the left side, and the value is tau x, and you know this convention again. This plane has a the surface for a normal vector of this particular plane is along x direction. That's why you have x, and the force is acting to the x direction, so that's why you have another x here. Tau xx, since this is a shear stress, you must multiply it with the area. It's dy dz. So this is the force. So pressure force, normal stress force. You do have a shear stress force on this and this faces, but those point in y and z direction. But here we are only concentrating to derive x direction force. So we are only presenting x components, forces in x components. And now again for the top and bottom faces, now you can see this is the top face, and I will use a different color for the bottom face. So this is the bottom face, and you know that, I mean, we have already studied on this top face. This is the direction of shear stress. It's tau yx plus, again I am writing top first, rather I should have written bottom first. Okay, it's a general mistake, sorry, habit. So bottom face, the force should be tau yx. Again, you know, this particular plane, normal vector, a normal vector of this particular plane is pointing along y direction, that's why you have y, and the force is along x direction, that's why you have x. Tau yx multiplied by area of this particular plane is dx dz, and when you apply Taylor series expansion, you get same thing again, tau x by del y dy multiplied by dx dz. So that's all on these two planes. Now again for the back plane, so this is the back one, back side, just letting you know this is the back side. And again for the front side, so you can see this is the front one. Oh, okay, so it's getting it will become ugly, so I will not fill it up. So I think the best way to do is A, B, C, D, E, F, G, H. Now the back plane is A, D, H, E. Now the bottom plane is, front plane. Here this front plane is B, C, G, F. So now on the back plane, you do have a shear stress which is pointing to the right side, which is pointing to the left side. So see, I made a mistake. So which is pointing to the left side. Why? Because we assumed horizontal force is increasing in the positive z direction. That means the fluid element which is back side of this one, so basically here, that fluid element is moving slowly when compared to this particular fluid, so that is trying to pull this one to the left side because relative velocity is pointing to the left side. So now the value here is, I'll just write here, tau zx dx dy, and on the front plane the shear stress points to the right side and its value will be tau zx plus the derivative from Taylor series expansion along tau z dz dx dy. So now after going through all this hard work, you can see that we wrote horizontal velocities on the left and right plane, horizontal forces on the left and right plane, horizontal forces on the top and bottom plane, horizontal forces on back and front plane. Now just if you guys have written down these expressions on your notebook, all you have to do now is just write the net force. That's all. So the net force that you can simply write it as, so I'll just write it here quickly. So you have P minus, this is the normal, this is the pressure force that I'm writing here, P plus del P by del X dx. This complete thing is multiplied by the area of left and right plane. So why did I write this one? We can just simply go back to this one, left and right thing. So P dy dx is pointing along x direction, and P plus dp by dx del x is pointing along minus x direction. So this minus this, that's what I had written. Yeah. Now I had written pressure. In the same way, I will just simply write the normal stress tensor. So I will write tau xx plus del tau xx by del x dx minus tau xx multiplied by the surface area of left and right planes. Again, how I have written this one, it's straightforward. So you see this thing, this normal stress force which is pointing to the positive x direction. So this is pointing to the negative x direction. This, so this minus this. That's all. Now we will just add all the forces. So we will write this one, and we will write back and front. So I'll just go on writing that. So plus, now for the top and bottom faces we will write, so tau you can write yourself. I'll just, oh come on, okay, I'll write here del tau yx by del y dy minus tau yx, this multiplied by dx dz plus, so again on the back and front planes tau zx plus del tau zx by del z dz minus tau zx multiplied by dx dy. So this is the net surface force. Now we haven't mentioned the body force. The body force is, you have to add all forces, right? For the body force you can just simply add okay, what is the body force? Body force, if it is a gravity, you have to write mass multiplied by g, but that particular body force, mass multiplied by g is the acceleration, acceleration due to gravity. So assume, let's make it a general term. So because we are trying to, okay, let's make it gravity for the time being. So gravity, g is acceleration due to gravity, and mass, what is the mass for this particular element? Mass of this particular element is density multiplied by volume, dx dy dz multiplied by acceleration due to gravity g, and you guys know acceleration due to gravity points only along y direction. So assume we are in some 3D space, and this acceleration due to gravity has x, y and z components, and this is the x component because we are only trying to write x components. So this is x component. So this is the body force. These are above I had written all surface forces. So these are all surface forces. This is body force. Now this complete force, this complete thing is equal to net force acting on this particular fluid element along x direction. We will write the expression for this one later. Now you can clearly see, you can strike this one out, you can strike this one out, this one, this one, so you left down with the other expressions. Okay, so now let me write fx. So fx, this is the net force. So from Newton's second law, you know that fx is mass multiplied by acceleration of a particular body. So now this fluid element has some acceleration and it has some mass. Again, remember that mass and acceleration is different from this body force. This body force rho dx dy dz gx is because of the force exerted by the gravity on this particular fluid element. So by combining all these particular forces, there is a net effect, like the behavior, the one that we are writing here is the behavior of this particular fluid element because of the forces, because of all these forces. By combining all these forces, there is a resultant behavior on that particular fluid element. That resultant behavior can be written as dx dy dz multiplied by acceleration. So this is mass, this is acceleration, and again you know acceleration is du by dt. Here we are talking only about x-axis, so we don't need to write this vector x component, we don't need to write this one. So this is rho dx dy dz multiplied by du by dt. At the end, when you combine all these things, you can simply write, so you can simply write rho dx dy dz. This is a derivative of velocity with respect to time. This is a complete derivative, by the way. This is from standard calculus, where we write velocity is nothing but acceleration is nothing but rate of change of velocity. So this is the complete derivative is equal to, now we have these terms here, net terms here, so we just need to simply write them down here. So you will get final result as minus dp by dx dy dz plus del tau xx by del x dx dy dz plus del tau yx divided by del y dy dx dz plus del tau zx divided by del z dz dx dy plus rho dx dy dz gx. So you can simply strike. So there is a resultant equation here, which is this equation, the very first equation. Did you guys see this? So the resultant equation, we just simply considered a control volume and we applied all forces. We just simply considered a control volume. We basically used a sign convention for velocities and considered all forces and its directions on all faces of that particular fluid element. On all faces, the surface forces that are acting on all faces plus the body force and the net resultant behavior of that fluid element. So we simply got a final expression which is same as this expression. So here fx is nothing but gx there. Similarly, as an exercise, you guys should do y velocity on all faces again. Consider the pressure on the along y direction, which will be only present on top and bottom face, and the shear stresses which will present on all faces. Consider only the y components, and then rho gy you will get the second one. If you consider along the z direction, you will get the third one. So this thing, you guys can see this is not written in conservative form because of the presence of the substantial derivative or the Lagrangian derivative. So here Lagrangian derivative means you are moving with the fluid particle, and if you may recall, in the very beginning we have mentioned that moving control volume. So you have the Lagrangian derivative. So this is called Lagrangian frame of reference, or you can simply say this is a substantial derivative, which is just a term given, but Lagrangian derivative is more formal. That I'm not sure whether you have studied that or not. So just remember that one. Now, while talking with while considering with the mass equation, yeah,
That's the question.
yeah, tell me.
Well, F and G are the same, like Fx and Gx.
Fx and Gx are the same. Fx is just a general term that Sarang has used. That's all. I see. In order to give you a clear, straightforward information, I considered acceleration due to gravity, which is denoted by G. That's all. So what I was saying. Okay. So in conservation of mass in the last class, I am assuming that you guys have considered non-conservative form and conservative form, and Sarang must have showed you how to get non-conservative from conservative form and the other way around. If you guys remember or not remember, we will just quickly go through the same thing for the momentum equation. So in this particular case, in the particular derivation here, you can see I have mentioned moving control volume, and also you are seeing this equation, final equation, which is along the x direction. So this is a substantial derivative, and this is written in a non-conservative form because of the presence of Lagrangian derivative, and also because we have derived this by considering a moving frame, moving control volume. So now let's try to see whether we can get a conservative form from this one or not. Simply put, there are some following some basic vector calculus principles. So here we have considered the left term rho du by dt is equal to, so this is the substantial derivative definition. So capital du by dt is nothing but del u by del t plus v dot grad u. So here this v is a vector, this u is an x component of the velocity field. So now we want to simplify these two terms, rho du by dt and this one. So how can we do that? So we know, okay, now we have du by dt is equal to del u by del t plus u dot del u. So that's what it is written. I just removed rho. So okay, I should not remove rho, I should write rho, because that's the complete, that is exact term. So, and without that we won't get conservative form. So now let's look at this one, rho du by dt. What you can do is, if we consider rho u, like differential of rho u by del rho u by del t, if we use like derivatives approximation, so I mean, basically you are applying a temporal derivative on this rho u term. So from standard definitions you can simply write this as rho du by dt. This is u del rho by del t. So you simply have this expansion for this derivative, and now you have rho du by dt, which is this term. So this term is equal to this minus this. So we will be substituting that there. Just keep that in mind. And now similarly for rho u grad u, what we will do is we will consider this one again. So let's see. Okay, that one is done. Okay, so so this is actually oh, I'm sorry, I wrote it wrong. I wrote it with respect to time. So okay, let's look at this one more clearly. So this is u dot grad u. This is nothing but rho u du by dx plus rho v du by dy plus rho w du by dz. So that is the expansion for this one. Now, so what is this? Okay, it looks like I'm doing a component wise thing. This is going to be long. So if you do it in vector notation, this is going to be straightforward. So I will just do for this term. I want to explain you guys a bit clearly, so I will just do for this term. So this term, if you guys can write this one, okay, consider again, push these two inside, just assume both of them are inside. Rho u by del x, this is equal to rho u du by dx plus u del rho u by del x. In the same way you can write for this one. You can write for this one and this one. Just push these two inside. So basically rho v u by del y is equal to rho v del u by del y plus u del rho v by del y. So you guys simply have this one. Same thing you will get for this one. So my point is, when you have, so basically you have this, okay, sorry, basically you have this term in here. In the actual convection part, these are the terms that you have, and you'll get the third time when you do this one. So what I'm going to do is I'm going to replace this and this with this minus this minus this, and you'll get this minus this. When you actually write that one, what you will finally get is, so del of rho u by del x minus u del rho u by del x, this is one term you will get, plus del of rho v u by del y minus u del rho v by del y, this is another term, plus similarly you will get for the z axis, you will get del by del z of rho wu minus u del by del z of rho w. That's what you will get. So all we did here is we have this term, we want to replace this one with this minus this, and we want to replace this term with this and the third term. So that is all we are doing, nothing else we are doing. So when you actually substitute, what you will get, so I'll just simply consider I'll just rewrite that del u. It's okay. Sorry. So du by dt. This is the actual expression we had above is equal to. Now let's go back. We have rho du by dt. We want to replace it with this minus this. So we can simply write del rho u by del t minus u del rho by del t. This is one term plus this term and this z term. So let's consider this term. Okay, I'm just simply copy pasting, nothing as I'm doing, plus this term, and similarly for z term you'll just need to write those terms. So now when you these are all whatever I'm doing is just simple manipulations. So write this one del rho u by del t plus just combine these terms del rho u by del x. So what I did is I combined this. Similarly there will be another term plus del rho vu by del y plus del rho wu by del y. We wrote the first terms, this one and first term from the other things. So this plus, now we need to write these things. So you have actually minus there, we can simply choose to write minus here. Just write minus, you can just simply take out minus outside, and then you will get u del rho by del t plus u del rho u by del x. So I took minus outside, plus u del rho v by del y plus w rho del rho w by del z. This is what you get. And if you guys remember, if you take u outside, del rho by del t plus del by del x of rho u plus del by del y of rho v plus del by del z of rho w, that is conservation of mass, which you have derived in the last class. That means this complete thing is equal to 0. So the left hand side rho du by dt is nothing but this one. This is written in conservative form now. So okay, whatever that's presented here is same as exactly what I derived. So basically when you put all together, you get rho du by dt is equal to this complete term. I think there is a final, okay, there is an expression here, rho du by dt plus rho u square. Rho u square is rho, I had written rho u here, which is rho u square plus rho uv and rho uw by dc. So this is the left hand side of the x momentum equation. This is not the x momentum equation, this is the left hand side of the x momentum equation, and the right hand side is whatever we have derived above, which is this part, pressure term, shear stress tensor, and the body forces. So this is the complete derivation of the x momentum equation. I think you guys should go through the you guys should try the y and z axis, z directions. So are you guys fine with whatever I just said? I think it's a lot to cover, but I just tried to cover, and it requires practice, and you guys should ask questions in the next class again. Any questions related to what we have discussed just now? When we are done with that, I'll just quickly open Octave and then show you guys. Any questions?
I think we have another 5 to 10 minutes.
Sure. So any questions on the conservation of momentum equation?
Did you guys?
So conservation of momentum equation, I mean it's one of the fundamental equations. So I mean, all I simply did was I just considered a fluid element for forces, just balance, nothing else. And then used some mathematical manipulations, used conservation of mass, and then got the converted non-conservative form to conservative form. That's all I did. You guys can go through the slides or go through the textbook, reference textbook, and you guys should practice the x y deriving the y component, and then ask any questions in the next class. That will greatly help. It's just hardly, it will take half an hour, so it's worth spending. So this is about momentum equation. Now I think it was mentioned to discuss the programming now. So did you guys install Octave? Okay. uh, how many of you installed Octave on Linux, on Ubuntu or Linux, any Linux, it doesn't matter.
I think everyone installed Octave on Windows.
Okay, all of you installed on Windows. Okay, I actually installed on Linux, so I think you guys can see my screen. So what I did is I installed a VirtualBox on my operating system. I have a Mac, and I installed a VirtualBox on that. And inside VirtualBox, I installed basically Ubuntu, which is one of the Linux flavors. So on inside Ubuntu, I installed Octave. So if you guys have installed Octave directly on Windows, that's well and good. So the reason why I took this route is you will be working with OpenFOAM, and it is built on Linux systems, a system. It is written on Linux system, and later on I think they might have made it cross-platform compatible, or they must have had executables. I never worked with Windows for OpenFOAM, but it is extremely easy and straightforward to use OpenFOAM on Ubuntu. So it's a good practice right from now. If you guys can install VirtualBox, which is already posted, the link is already posted in the course page. Just go there and then install it, and inside that install Ubuntu, and inside that install Octave, because we will be installing OpenFOAM also in that one. So if you guys have any trouble installing or need any guidelines, you can ask any of us, like Sarang or me, in the next class or anywhere, or even in the WhatsApp. So I can try to make a tutorial or some sort of PDF. Yeah, I can guide you guys. There's no problem at all. Okay, that said, I'm just waiting for this guy to start. And another advantage is, like you guys know, Windows will hog memory, like will just consume memory like anything. So if you guys install virtual machine, you can just simply that virtual machine, delete that virtual machine, and everything, whatever the temporary software that you have installed, it will all just go away. That's a nice thing. Okay, now if you guys can see the screen, this is the Ubuntu frame, and this is the terminal. You guys need not know about these things right now, but you will need while working with OpenFOAM. This is the Octave. I installed Octave, and this is the Octave. So it's opening, so few seconds. Okay. So all of you can see the window, right? Just quickly go to this one. Okay. This is the command window where I am actually typing the commands. That is the command window. And here you can see this thing, just like in Windows you have the address bar, right? File explorer bar. Same thing, it says in which directory you are in, current directory. And this is the file browser, so same as in Windows, in the left hand side you will see. So this is the folder in which I am currently present, and this is the I am currently present in this folder GNU Octave, and inside that I have a folder called EDX engine -CFD. And this is the workspace. You will see about workspace soon. And this is the command history. So whatever the commands I just typed, like CLC, exit, everything is sitting here. So you can go through the list of commands that that you must have typed earlier. You most certainly it's very rare that you will be using this window, but workspace is important. Okay, so in Octave basically it's just another programming software, programmable software, and Octave is the sorry, yeah. So Octave you can treat it as a language also. So it's written on top of C and C++, and some, okay, I don't think there's Java involved here. So for example, you have a variable a is equal to 1, so you want to assign. So all of you, do you guys all know basic programming like C programming? Yes, okay, yes. So basically a is equal to 1, so you will write int a is equal to 1 in C, float a is equal to 1.0, things like that, float and double. So basically here everything is double precision or float precision by default, and a is equal to 1 when I press, so a is equal to 1. So if you, as you can see, when I typed a is equal to 1, it just outputted a is equal to 1. It just tells us, okay, this is what you typed. If you don't want that to be displayed, you can just simply type a is equal to 1 semicolon enter, so it won't display, but a is still there. You can see in workspace a is the variable. So if you want to get the value out of it, type a and then press enter, you will get a is equal to 1. If you type CLC, it will clear everything in this from this command window. That's all. It will not clear from the workspace. If you want to clear from the workspace, you have to do clear. So if you do clear, see A is gone. So that's just a brief overview. And also arrays, you can write, let's write a in your first homework problem, you must have seen some examples, 1 2 3 4. So from basic math you can see that from matrices class, you know that this is 1 2 3 4 and this is a row matrix. It has 4 columns. So you can see this has 4 columns, 1 2 3 4. It's written in a column, it's printed in a column way. So you can see this is a column matrix. And if you want to get a row matrix, all you need to do is replace commas with semicolons. So you will get a column matrix, I'm sorry. So you will get a column matrix. So this is one column, so it has 4 rows. So this is basically 4 by 1 matrix. This top one is basically 1 by 4 matrix. And for us to convert this 4 by 1 to 1 by 4, you just need to simply do transpose. Transpose is denoted by this. So A transpose is 1 2 3 4. That's all. So you can do multiplications, A multiplied by A transpose. So A is basically A is still this, you just outputted A transpose. It is stored in a temporary variable called answer, but A is still a column matrix. So 1 2 3 4. So the size of this is 4 by 1 and A transpose size is 1 by 4. So when we do A multiplied by A transpose, we should get a 4 by 4 matrix. So we got 4 by 4 matrix. And if you want to find eigenvalues of this one, so we can simply write eigen of answer. So basically I haven't saved the result of A transpose in any variable. It is automatically saved in a temporary variable called ans. It is a good practice to actually store this in a different variable, but I will show you that. I will just show you this usage of this one. Eigen of answer will give you eigen vectors basically. So okay, let's do this again. B is equal to A multiplied by A transpose. So I'm truncating the output by using a semicolon, so it's not printing the output. If I want to see what's stored in here, in B, it's here. Now if I want to get eigenvalues of B, so here, so E is the eigenvalues, this gives the diagonal values are the eigenvalues, V is the eigen matrix. So what this tells you is each column here, this is the eigenvectors pointing along each direction. So okay, it has been a while for me to for me that I have used, so I have been a bit not so sharp in this one. So let me do help here. So what help does is it tells help eig. So it gives us the usage of the function eig. So help space eig, it gives us it tells us, okay, so computes the eigenvalues. So it returns two outputs, v and lambda, and also it returns one output. If you are not giving, if you are not asking for two outputs, it returns by default only one output. So what is v and what is lambda, that is not written here correctly. Okay, basically v is eigenvectors, lambda is eigenvalues, so it is not given clearly in this help. So basically the help of Octave is not clear. So if you are using MATLAB, that would have been very clearly given. But anyway, v is eigenvectors, lambda is eigenvalues. So you know that when you have a matrix B, how do you guys derive eigenvalues? You write B minus lambda I is equal to 0, and then you will get 1 minus lambda, 4 minus lambda, 9 minus lambda, 16 minus lambda, and when you take a determinant of that, you will get a fourth order equation. When you find the roots of lambda, you will get some values, 4 values. Those 4 values are these values. So I'm just talking about eigen, but I need not talk about that. This is Octave. So that's all. Like this is about using command window, and you have a editor here, so you can write a program here also. So a is equal to 1, b is equal to 2, c is equal to a multiplied by b, and d is equal to 1 2 3 4, e is equal to 2 3 4 5. So all these things we can save in some folder, sample. So basically in this particular folder it is there. So now when I try to execute this one, so basically it will, what this does is it assigns a variable a is equal to 1, b is equal to 1, it tries a c is equal to a multiplied by, so c is equal to 2 here, and it creates two arrays, d is equal, column matrices d and e. So but it won't display anything in the command window. But if you want to display in the command window, let's do d multiplied by e transpose. So f is equal to d multiplied by e transpose, and I did not truncate with the semicolon. So you will, when I run this code, you will get the output of this one. So let's run this one. You have this save file and run. So when you click this one, you will see a warning here, change directory, add directory to path. So let's cancel this. What does that mean is, you are in GNU Octave directory, and it has a folder called edx engine CFD. Inside that there is sample.m. So the compiler for Octave could not find sample.m. So it has to find it. It has to load this particular file. That's why it gave an option, add directory to load path. So either you can click this and it will run automatically, or the other option is, so let's undock this so we can move this one here. Okay, there is another thing. So either you work here by changing this, switching between these two, command window and editor window, or you can undock this and then work only on command window, anyway whichever is comfortable. So in order to add sample thing, you can simply write add path of /edx engine -cfd. Either you can do this, or you can simply type this and then add directory to path. So simply both of them does the same thing. I choose the GUI based option. Now if we go to command window, what it will output is, it will output the result of f. So it outputted the result of f. Since this was a world command that I had written but I did not clear, it was still there. So f value is this one, and all variables are being stored in the workspace, a b c d f, everything. So this is a simple introduction, and this is about windows of this Octave. So just practice on this one, and this is programming, you must practice. There is no other way to learn programming. So you guys will surely have questions on this one, because I just quickly went through within 10 minutes. If you guys have any questions, you can just ask. Otherwise, we are simply done with this particular demo. You guys practice and then ask questions.
Yeah, so I think
Actually, I have installed Ubuntu partition.
okay.
Without installing virtual box.
Okay.
It's okay, right?
Yeah, I think it's okay.
Of course, it's okay. So